Yeah.
Oh, okay, okay. Is that good now?
Yeah.
All right. So I was saying that since nodes often have attributes, one might want to learn and exploit the correlation between node attributes and neighbor attributes. However, in many practical applications, the network is not readily available for this kind of investigation. It has to be collected first. It has to be sampled. So this brings us to the theme of his thesis, which is the use of sampling estimation to characterize networks and to design network algorithms. So the rest of this talk is organized around the technical chapters, 3 technical chapters. Since we have already discussed chapter 2 in length today, I'm going to summarize the results for that chapter, but focus really on the chapter 1 and 3. Okay? So chapter 1 regards the characterization of networks using multidimensional random walks with jumps. We want to be able to answer this question: how to estimate node label distributions from samples. First, we have to understand how a network can be sampled. So sampling is crucial to characterizing large-scale data, and for networks, the sampling strategy is going to depend on the API to access nodes and edges.
Could you define what characterizing a network is?
Okay, sure. So you might be interested in estimating the fraction of nodes that have a particular label, or identifying substructures in the graph. All those things could be thought of as characterizing networks. So here in particular, we are interested in node label distributions.
But it could mean any number of statistics that you would want to estimate on a network.
That's right, yes.
Okay, but it does not necessarily refer to gathering all of those, but some subset down to perhaps a single distribution that you want.
That's exactly right.
Okay.
Yeah, I'm just sort of introducing the larger context in which this work is included. Okay. So the sampling strategy is going to depend on sort of this API. So for you can use a software called traceroute to sample computer networks by sampling all the routers on a path between your computer and an IP on the internet. You might be able to do uniform vertex sampling in social networks if you know that the user IDs have a given number of bits. Then you can generate these IDs at random and check whether they correspond to a valid user or not. This is feasible when the ID space is not sparsely populated, or when a specific API exists for retrieving nodes informally. Random walks are also another way of sampling graphs. And you can use that, for example, on web graphs and social networks. And in the case of undirected graphs, the random walk is going to sample nodes in proportion to their degree when it reaches a steady state. So in the case of directed networks where incoming links are not directly observable, things are more complicated. So for example, when you're visiting a web page, then you can see the outgoing links, but you don't know the pages that are pointing to the page that you're visiting. So a classic random walk would incur biases, observation biases on this type of network that can only be removed by conditioning on the entire graph structure. But that defeats the very purpose of sampling. So a couple of techniques have been proposed to sample directed networks. Much larger set of techniques have been proposed for undirected networks. As the first contribution of this thesis, we propose a sampling method that is suitable to both undirected networks and directed networks regardless of the incoming edge's visibility. Okay? So this method is called directed unbiased frontier sampling, or DUFS for short. And it uses random walk-based sampling. More precisely, it uses a large number of coordinated walkers, which are initialized uniformly over the vertex set. So to determine the initial location of each walker, we're going to sample a node uniformly at If incoming edges are unobservable, this method constructs a virtual undirected graph over which the random walkers are going to move. And because of that, it's possible that the random walk traverses some of the edges from the original directed network in the reverse direction. At each step, DUFS selects the next walker to move in proportion to the degree of the node where it's currently located. So with once the walker is selected, the walker is going to perform a random jump with probability equal to that, where W is a parameter, is the random jump weight, and deg of V is the degree of the vertex where the walker is located in this virtual undirected graph. So with this probability, the walker is going to perform a random jump and land on a node chosen uniform at random. And with 1 minus that, it's going to move to a random leader. So part of it is borrowed from shear sampling, a method proposed for undirected networks. And part of it is borrowed from directed unbiased random walk. The sampling cost is set to be 1 whenever you move a random walk and observe a new vertex. And the cost of uniform vertex sampling is C for some constant C greater than or equal to 1, representing the fact that uniform vertex sampling is typically more expensive than moving a random walk on the graph. We incur this cost C when we initialize the walkers, and also when we perform random jumps. Okay? Is that clear so far? All right. Once we get the random walk samples, which are essentially the vertices we observe, we can combine that with information contained in the initial walker locations, which are essentially uniform vertex samples. And in order to do that, we propose a hybrid estimator that takes this kind of samples and outputs a node label distribution estimates. Okay. We show that this estimator is asymptotically unbiased. And in the specific case where the labels we are interested in are the degrees of the nodes in the original graph, then if you know the average degree, this estimator becomes the minimum variance unbiased estimator. Despite the fact that we rarely know, we typically don't know the true average degree, this tells us that if our estimate for the average degree is close to the true degree, then our estimate should be accurate compared to other unbiased estimators. So as another contribution, we investigate the effect of the DUFS parameters on estimation errors in order to propose practical guidelines on how to set them under different scenarios. The scenarios we consider vary according to the in-edges visibility. In some cases, we see both incoming and outgoing edges. In other cases, we just see the outgoing edges. The cost of vertex sampling also varies. So we consider C equal to 1 and C equal to 10. The parameters of this method are the total budget, which we fix to be 10% of the set of vertices, essentially because we have a good understanding of how the accuracy of the estimates vary as we change the budget. So we actually look at other parameters. We thought about using the number of walkers as a parameter, but it turns out that the number of walkers, it makes sense to use more walkers when the network is larger or when the budget is larger. So instead of using that, we relate the number of walkers to the total budget using the budget per walker as a parameter. So that's essentially the total budget minus the cost for initializing the walkers divided by the number of walkers. You can think of that as the average number of steps a walker performs once you initialize it. And the last parameter is the random jump weight, W. So the larger the W, the more likely we are to perform random jumps. At the beginning, we thought that maybe if you use small b, or equivalently a large number of walkers, then you're not going to need to perform random jumps, right? Because it's already going to cover possibly multiple connected components of this graph. when you initialize walkers at random. But it turns out that this is not the case, as I'm going to show you in this next slide. So here I have typical results for the out-degree distribution estimation when the incoming and outgoing edges are visible, and C is equal to 1. So this one in particular is for the Flickr links data set from the Stanford Snap repository. And here, the number of vertices is roughly 1.7 million, number of edges is 22.6 million, and the budget, as I said, is set to be 10% of this number of vertices. So what we see here is the normalized root mean square error on the y-axis for different out-degree values. And here, I'm plotting 9 curves that are combinations of the random jump rate and the budget per walker. So the blue blue is W equal to 0.1, meaning that we're rarely performing jumps. W equal to 1 means we're performing, let's say, some jumps, and equal to 10, we're performing frequent jumps. So the solid curves indicate B equal to 1 step on average per walker. B equal to 10 steps and 100 steps. Since the budget is fixed, as we go down here, we are also decreasing the total number of walkers. Okay? So what we see here is that for, let's say, large out degrees, then this green dashed and green dotted curve are the ones that are achieving the smallest error. So this corresponds to performing some jumps. Okay, so this is green, and using either sort of B equal to 10 or 100 steps per walker. And if you look at these two curves, they also show they exhibit good performance for low out degree values. And in general, it's better to set W equal to 1 than setting very low or too large when it comes to the large out degrees. So as the bottom line, the jumps can help estimation both in the head and in the tail, even though we're using a large number of models. Go ahead.
Many of the graphs in, I think it's figure 1.5, which is this is one of them, have this distinctive shape.
I knew you were going to ask that.
Did you talk about that?
Yes. So they look like straight lines. And that's something that you pointed out to me in my proposal, and I didn't know exactly why that was the case. So we went to look and investigate why there's this sort of linear relationship. Yes.
But that's not linear, it's not monotonic.
Oh yeah, yes, you're right. So parts of that are linear, and this has to do with the fact that at the tail, you're going to see many out degrees that occur only once. So if you could, I'm going to say that, if you could approximate this as a power law distribution, okay, and having the number of nodes grow to infinity, then this part will look like a straight line. And this is sort of a byproduct of the fact that we only see one instance of these nodes.
So do I recall correctly that there's actually 2 different estimation procedures around that for the head and the tail?
It's only one estimator that combines both, that combines both types of samples. But you can essentially decompose that into vertex sampling and edge sampling.
Because does something happen at 10 to the 3rd out degree?
Yes, what happens is after that point you only see one instance of each out degree. So what I'm saying is that if the network grows, okay, and it sort of follows the same trends, then you're going to see more instances, and this would sort of shoot up. Let me show you the next slides, and then you can tell me whether you are convinced or not.
Okay.
Okay. Okay. So to answer this question, we investigate the two basic processes that compose UFS, which are vertex sampling used to determine the initial walker locations, and edge sampling used as an approximation for random walk sampling. So we show that for degree distributions that follow power law, meaning the fraction of nodes that have degree L is given by L to the power of minus alpha divided by some normalizing constant for some alpha greater than 1. Then we show that the normalized root mean square error associated with vertex sampling is given by this formula, okay, which in the case where when theta L is much smaller than 1, which is true for large L degrees, then it becomes this square root of BZ L to the power of alpha. When you take the log of both sides, you can see that the
Z is a normalization.
Yes, it's a normalization constant. Is that?
No.
Okay. So when you take the log on both sides, then you can see that the log of the normalized root mean square error is a linear function of the log of the degree with slope equal to alpha divided by 2. And we can show pretty much the same thing for edge sampling. The only difference is that the slope is going to be alpha minus 1 divided by 2. And these curves, when you use the equality, then these curves actually cross in one point, but we are looking at the approximations for large L degrees. Okay. So here, I'm assuming that all the theta L's are given by this form. But this is not true for the data set that we saw, because at one point, essentially I have one instance of that of each L degree. Okay.
And that transition happens right at 10 to the third?
For that data set, but for other data set, it's going to be another point.
Okay. The other question I had on those graphs is, when I see errors like we're seeing, normalized root mean squared errors like we're seeing, are those large, small, in between?
Right. So
Some sort
ideally,
of absolute sense.
okay, that's a good question. A general rule for normalized root mean square error is that we want them to be below 1 for the error to be at least of the same order of magnitude than the true estimates. Okay, the true theta L's. Okay. And if we go back here a little bit, this seems to be the case for this data set, like a sample 10%.
Well, it looks like it's above 1 for half of the degree.
No, this is 10 to the
This is 1.
this is 1.
Thanks.
All right. So we also compute, we also quantify how much gain we get from the hybrid estimator. Remember that the original estimator proposed for Fujita sampling only uses the random walk samples, and here we propose an estimator that combines the initial walk locations with the random walk samples. The intuition that is that the hybrid estimator should be better at estimating labels associated with small in degree and small degree nodes, because the uniform vertex samples are more likely to land on degrees associated with large probability masses, which are exactly sort of small in degree and small degree. And this is exactly what we see when we estimate joint in and out degree distributions. So here I have the social network /dot for 82,000 nodes and 984,000 edges. And these parameters, what I'm going to show is the ratio between the error associated with the hybrid and the error associated with the original estimate. So points here correspond to pairs out degree and in degrees that are observed on this graph. And the color code is the ratio. So the fact that the spectrum is entirely below 1 means that the error associated with the proposed estimator is smaller than the error associated with the original for this entire distribution. And in particular for this regions where the out degrees are small and in degrees are small, then you see the largest error reductions. You see something from 5 to 13% in this area here. So the interesting thing is that the new estimate